And then many years later, in 1955, Emilio Segre and his collaborators at the Lawrence Berkeley Laboratory in California created the first beam of antiprotons by using a beam of protons striking a copper target, and they detected for the first time antiprotons. Those were the first proofs of the existence of antimatter.
Quantum physicists predicted the existence of antimatter, but until 1955, they couldn't make any. It seems the universe is filled with matter and very little antimatter. So the most reliable way to get hold of antimatter is to make it. That's what Fermilab does.
We create antiprotons by taking energetic protons and slamming them into a metal target. It creates enough energy density in the target that you can create particles, and there's a certain probability that you will create antiprotons. It's a very small probability, but it is large enough that we can actually create numbers that we can count. For every 500,000 protons that we put on the target, we can collect one antiproton.
This all takes place in the giant accelerator rings underground. They need all that room to get the particles moving fast enough before they hit the target to make antiprotons. After the antiprotons have been produced and collected, the stream of antiparticles must be kept close to the center of the tube and prevented from coming into contact with the walls.
We actually magnetically levitate it. We have a ring of electromagnets with a stainless steel tube which has all of the air evacuated out of it that's about 500 meters in circumference. And these antiprotons that are collected after these collisions with this target disk are put into this ring which we call the accumulator, and this tube is big enough and there's no air in it so that the particles can just sit there circulating.
They have to keep those antiparticles isolated, because if they come into contact with the particles in the wall, they will annihilate each other. So it would pose a big problem for beings like us, who are made of matter, if there was more antimatter in the universe.
It's a good thing that there's not equal amounts of matter and antimatter in the universe, because if I was to sit here in this chair and my antimatter counterpart came up and touched me on the shoulder, that would be the end of us and a good fraction of where we're sitting.
Matter and antimatter combine in a virtually perfect conversion of matter to energy. In other words, 100% of the matter and the antimatter become energy. Even in the best fusion reaction, perhaps 2% of matter becomes energy.
Antimatter is really the perfect form of energy storage because you get all of the energy out of the matter and the antimatter if you can make them annihilate. And that's a tremendous amount of energy. But a tremendous amount of energy is exactly what we need if we're going to power an interstellar spacecraft.
So how about using that tremendous energy for fuel?
Suppose you had 1 pennyweight of antimatter. That's 1/10 of an ounce of antimatter. The amount of energy in that 1 penny worth of antimatter would be enough to launch the space shuttle 60 times.
So how many miles per gallon would that be?
If you had antimatter gasoline, you'd be able to travel 40 billion miles per gallon, and that's not even fixing your car up.
Great mileage, except that our nearest star neighbor after the Sun is in the Alpha Centauri star system, 4 light years away. That's roughly 500 gallons, or 30 tanks full to travel to Alpha Centauri. We humans will have to speed up our antimatter production if we want to make a trip like that. Although Fermilab has been making antimatter for over 30 years, stocks are tiny.
Fermilab has 1/trillionth of a gram of antimatter stored in its accelerators. At the rate at which we make it, it would take us about 40-some million years to make 1/4 of a gram of antimatter.
That means it would take billions and billions of years for us humans to make enough antimatter fuel to get to Alpha Centauri, unless we learn how to make it faster. Or we could just steal the alien antimatter supply and their engine. The aliens who designed the ship we found have solved many dangers and drawbacks associated with antimatter fuel. First, they solved the problem of antimatter storage tanks. Our alien ship has a miniature version of Fermilab's magnetic accumulator. The aliens also solved the problem of fuel supply. Either they've found a source out in space, or they can create it on a large scale, because they've got a huge supply of antimatter on board. But as we solve one riddle, we encounter another. This alien spaceship clearly has turrets for weapons. What are those for? Attack or defense? What do our alien engineers intend to do to us? Weapons of mass destruction appear to be a standard feature on our alien spaceship. That's disturbing, but not really surprising. We'd like to assume any alien visitors would be friendly, or at least not belligerent when they touch down on Earth. But the aliens who built this ship would rather be safe than sorry. How else do we explain these death ray laser beams built into the ship? Come to think of it, it makes perfect sense when you're penetrating space. You'll never know what you'll run into. Maybe you'll encounter hostile creatures along the way. Like us. We're fairly hostile, and we have our own futuristic weaponry. Naturally, they involve laser beams too. And we don't need alien technology. The US military is working on several directed energy weapons.
A laser is just a device that allows you to send out a very coherent beam of light. If you think of a laser pointer that's used commonly now for briefings and stuff like that, it just allows you to get a very intense beam of light that goes a very long distance in a very small area.
In fact, the term laser is an acronym for light amplification by the stimulated emission of radiation. Focusing a laser is so simple, it's child's play.
If you recall when you were a kid, you probably had a magnifying glass, and you used to use the sun to put a beam of light on a leaf or maybe even a bug, and you could create a lot of heat. That's what you basically do with a laser. You focus that beam of light on something that you'd like to damage or destroy, and you hold it in place long enough to heat it up and damage it or destroy it.
Lasers make excellent weapons for two reasons. Firstly, laser beams travel at the speed of light, since that's what lasers are. Secondly, they can be aimed and focused with incredible precision. Not a lot of collateral damage with a laser beam. The first laser was actually a maser, developed in the mid-1950s. It didn't use visible light, but instead harnessed microwaves and ammonia gas to create a beam. But by the late 1950s, optical lasers had been created, and today they're everywhere.
Lasers are used in CD players, they're in dental drills, you use lasers in measuring devices. Lasers are everywhere pretty much.
Lasers can differ by wavelength or power. Most commercial lasers are powered by less than a watt of electricity. Military lasers are stronger. At the Laser Effects Facility at Kirkland Air Force Base in New Mexico, they can be much stronger. They have to be. Their job is to blow things up, or cook them at least.
Exo 1, laser on and fire.
The laser is called EDCL, and it basically stands for electrodischarge coaxial laser. It's a carbon dioxide laser, but we use 3 different gases to facilitate making the laser beam. We use helium as kind of a lasing medium, and then we use nitrogen and carbon dioxide.
You can't see the beam itself. The laser light is being emitted in the invisible infrared region of the spectrum. Kirkland's staff study the effects